Good morning. I'm not Casey. This is Casey. Do we have some slides? I just want to give a quick introduction to, there you go. Thanks so much. My name is Justin Pickar. I'm a Senior Director of Origination and Policy at Geronimo Power. My role today is to moderate, but also to introduce a little bit about my organization, my company that I've been with for about 18 years now. Next slide, please, or maybe I have the clicker. Thank you. Geronimo Power was founded in rural roots. The founder of our company was from Southwest Minnesota. The late Noel Ron is no longer with us on this earth, but he instilled the fabric of our organization, which is farmer-friendly, rural economic development. And that's something that instilled into me and is instilled into many that work for the organization today. The big update of Geronimo Power is that we're no longer National Grid Renewables. Geronimo Power's, we are currently owned by Brookfield, a small little equity shop that is very diversified. And here's a map of all the assets. We currently have 126 billion assets under management, 45 gigawatts of operating capacity, and 227 gigawatts of projects in the development pipeline. I think what Brookfield provides Geronimo Power is just a very strong backbone of capital to deploy our projects where we are developing projects, which is, right, SPP, MISO, PJM, MISO South. A little bit of the evolution. Many of you have seen this before, but I've been around the organization since 2007. We were founded in 2004 when Noel Ron was approached by a developer to put wind on his ground. And he said, you know what? You're taking advantage of the farmer. I'm going to do this myself. So that's when Noel Ron started the company called Geronimo Wind Energy. In 2009, we struck a deal with Enel Green Power North America. In 2019, National Grid purchased Geronimo Energy. And most recently in 2025, here just in May, that acquisition was complete. Brookfield is now our new parent. Some of our leaders, it's the same leadership, same team. Our leadership team that I report to is the same folks. Blake Nixon's our president CEO, and our leadership team's been around the industry for quite some time now. As far as our portfolio, and then I'll get to the meat and potatoes of today's presentation with Casey, but our portfolio is made up of, as I mentioned earlier, SPP, which we'll get to. Can't wait to dive into some of those major topics. MISO South, ERCOT, PJM, that's where our development pipeline is. We do have assets, development assets in Nebraska, including Brock Solar, North Fork Wind, and be happy to talk to you about those projects in more detail. To SPP, Casey. Our next speaker is Cathey. He's VP of Engineering and System Planning at SPP Southwest Power Pool. Casey oversees SPP's strategic evolution as the organization works to integrate large new loads, renewables, and transmission solutions across the central U.S. Casey's been in SPP since 2006 and spends the majority of his time between large load interconnections, a very diverse group, and resource planning. Between us, we can field a baseball team. I've got 4 kids, you've got 5, and we could definitely take on the world champs anytime. Please welcome the very accomplished Cathey.
All right, good morning, everyone. Thank you for that. Okay, so I asked ChatGPT to develop a joke, an opener. And I don't know how I'm training Chat because it was, where are my glasses? You barely see all. My LASIK's wearing off. So I don't know how I'm training ChatGPT because most of the jokes that it came up with I cannot say in public audience. Like it's not, it would not be okay. But This next panel is about generation interconnection, queue, process, backlog, give y'all an update on where things are at, and introduce something fairly exciting for the industry and SPP as well that we're calling consolidated planning process. So I'll just go to it. But I did find one joke. I just had to prompt it about 4 times to be not so snarky. So I don't know why, but so here's one. Generation interconnection in Nebraska is kind of like dating. Everyone says they're ready to commit, but then you find out there's a study phase first. I thought that was okay. That was not too bad. So get right into it. Happy to be here. We've got a lot of exciting updates. SPP's sort of in everything lately, and the industry is just what's crazy is I thought we were busy 10 years ago. Didn't really know that was not busy. Lately, it's been a lot. So just the current process and interconnection all types. Wanted to kind of give. I'm not going to educate y'all on the I don't want to bore you on the overall process unless you want to be bored. But we have performed the generation interconnection process for a while, and it worked 10 years ago. And you can see that. We've got 35 gigawatts of installed capacity of wind, over 16 wind turbines, and that all went through the generation interconnection process. And so the last 3 or 4 years, we've seen a massive backlog. And so that's been kind of the hot topic in the generation interconnection space at SPP. And it's gotten a lot of press, and it's not just SPP. It's all the RTOs have some version of a backlog. But if you really step back and you think about what the problem is, we do a least cost, directly assigned, queue-based generation interconnection process, and it's FERC approved as part of our tariff. And so it's almost like you get in line at Kroger, and there's only one cashier, and you get in line, and you just process your groceries. Well, what happens when you've been to Kroger or Walmart and there's not enough cashiers and the line just backs up into the aisle? That's really what's been happening with the queue-based process. It worked when it was incremental peakers, or even 10, 15 years ago when it was wind turbines in Nebraska and wind turbines in Kansas, and it was incremental. It was 2 or 3 gigs, and we would be able to process it. It was never designed for this rush of everyone trying to get their groceries on a Sunday and you only have one cashier. It was never designed for that. It was never designed for a wholesale fuel mix change. And so the last few years, we've seen a massive queue, and we just could not process them. And this just kind of helps illustrate all of the various, what we call DICES the old way. So and DICES is this acronym. We love our acronyms. Definitive Interconnection System Impact Study, but that's the primary GI process. So in order to connect generation today in SPP, you have to go through this process. And it just illustrates how many days it takes. And it's like a line in Kroger, you have to process in queue priority order. And that's very important to the integrity of costs. But there's a lot of problems there. One is our transmission system is saturated. 10, 15 years ago, we actually had transmission capacity. Now we're using power more than we've ever used it, but we haven't really built transmission very much. We've built some, but we haven't really future-proofed growth, and we haven't really allowed for the amount of wind and solar that we can tap into, especially now with load interconnecting. So I want to walk you through kind of at least an analogy in the way I think about our cost allocation rules for GI. Imagine that you're on the interstate and there's gridlock. It's a lot of traffic, and you're coming up, you're driving, and the traffic is stopped. Well, that's the transmission system locked up. So the transmission system's locked up, traffic is stopped. But the way this queue-based process works in cost allocation is you're the last car to hit that traffic that requires another lane to be built. So the highway actually has to get expanded. And rather than everybody pay their share of the usage of that highway and that extra lane, you get hit with the bill. That's how it works. And so that seems crazy, right? You're the last one. All the cars are causing the problem. All the electrons are causing the problem on the transmission system. But since it's queue-based and it's least cost, and we're tapped out on the transmission system, the next generation interconnection request, you are, as the car, hit the need for expansion of the highway, you get hit with all the costs. And so obviously a lot of our generation interconnection customers cannot sustain that amount, because instead of a $7 million, which is typical around what survives in a generator interconnection agreement, you're hit with $200 million, $400 million, and you're directly assigned for that highway expansion. So you're directly assigned for extra high voltage transmission facilities that are necessary to be able to accommodate the next layer of generation interconnection requests. And at least that's, in my mind, the best way to illustrate what's been the problem with the GI process, is that it worked when we had transmission capacity. Now it doesn't work. It doesn't work because these individual requests cannot sustain that amount of dollars necessary to fund the transmission system. So we have different application requirements, but there's a success story here, and we're in the process of it. So I don't want to say we're in the clear totally, but we have a light at the end of the tunnel at SPP. So one thing that is kind of an old data point is that we've seen this backlog take some of our requests up to 6+ years to get through the generation interconnection queue. That is thankfully an old data point. So when you say, I can't connect to SPP anymore, it's going to take 6 years, that's not true anymore. And so this helps illustrate that time frame. And as you can see on the, let's see if this works. Okay, as you can see, the DICES runs in 2018, those requests took 6 years to process. So you can sort of see, just based on a timeline, when we started getting that backlog and started saturating the, not just because of large queues, but also, like I said, the transmission system was locked up. So it was locked up and we couldn't process anything. And when I say we couldn't process anything, if you're in the room and you've run power flow or any kind of models, it wouldn't even solve. It was so much generation on top of already saturated grid. It didn't know mathematically what to do. And so we had to scramble, not only from a engineering perspective and modeling perspective, but also from a policy perspective, and changing our tariff in order to be able to get through and unclog the queue. And so in 2021, I guess 1 year into the pandemic, we basically said we're fed up. We cannot. This is not working. And so we developed what we call the backlog clearing plan, and we filed with FERC in February, and they approved it. And without getting too technical, it was almost like a waterfall approach. So we took all of these backlogs and we squeezed 7 years of backlog into 3, and we processed those in a waterfall approach based on the phase that I walked through with those timing. So effectively, we shrunk the time frame to get through the backlog. We still maintain integrity of the purpose of it is really to make sure that you're assessing the reliability of the grid and making sure that these generators can connect reliably. And so we want to make sure you still have the integrity of the overall study. But as you can see, we shrunk each year. We got better and better and better. And then at the same time, this gold bar is the number of projects that we processed. So we were getting faster as we were getting more volume, that's an achievement for us. And so we're real happy to be in this mode where now we're still processing these last few green bars, but as you can see, the average to get through the queue has consistently dropped. So gone are the days that it takes 6 years to get through the GI process. So we're really proud that we're not in that mode anymore. And quite frankly, we have to be faster. That's one piece that we're really looking at SPP is we have to build infrastructure. We have to be faster for load connection, these load customers, and economic development. We have to be faster for generation connections. We have to be faster for transmission. But it's not just transmission build. I want to spend a little bit of time on that. It's also transmission capacity and capabilities. We have to be able to extract as much value of our existing grid as possible. And there is some low-hanging fruit that we can extract so that we can maximize what we already have while we build more infrastructure to be able to sustain reliability, maintain reliability, the economies of scale, and basically what We just heard from a plan and reserve margin and making sure we balance when wind drops or the sun's not out, then you can access thermal generation and you can use the overall economies of scale for the overall grid to maintain reliability. So this right here is a success story. And as you can see, over 400 requests, and that's climbing. And so we're still working through, but we're on track. We're on pace to have the next DICES. These are the numbers of what the DICES is, not the year it actually took. So 2024 DICES we're actually doing in 26. We've debated on whether or not we need to just rename it because it's actually taking place in the calendar year of 26. But we're on pace to be 1.5 years, which is significantly less than the 6 years that it's taken in the past. So that's great. Then on the bottom, it shows you the sheer volume of not just the counts that we're processing, but also the capacity that we're processing. And just from a frame of reference perspective, SPP as a region peaks at 52 gigawatts, and the state of Nebraska is around 7 of that. So when we talk about installed capacity in a single study of 18 gigs and processing 22 gigs, that's a significant amount of generation that we have to process. Now, not all of that's going to survive. And it's unfortunate, but it's because of what I mentioned earlier. It's because depending on the location, these generators hit these constraints, and then they get hit with what we call shared network upgrade charge, and they get hit with a significant fee to build because they're kind of the straw that broke the camel's back, so they're causing the need for upgrades. But it's still significant, and there is a decent amount that's going to survive there. Okay, so the state of the queue. Usually when I speak, the first thing that people ask is, what's in the queue? I wanted to kind of be dynamic here, but the laptop isn't connected to the internet. You can go on SPP's website and go to Engineering, Generator, Interconnection, and then click on the dashboard, and it's a dashboard you can play with. And what I mean by that is it's active, and you can click on the state, and you can click on generation type, and cluster. You can filter on these things, and it's dynamic. It's updated twice a week, so it's very up to date. In fact, this screenshot's probably already old because it was just made a few weeks ago, but things move fast lately. I did pull the numbers, though, for Nebraska. Unfortunately, I didn't put them in the screenshot, so let me pull that right now. So from a Nebraska perspective, we are seeing a decent amount of thermal generation now. Total in the queue for Nebraska is 13.5 gigawatts, which is really large. That's great. 6,200 megawatts of thermal. Wind is 1.3 gigawatts. A lot of battery storage. So I was joking with Joe. Where's Joe? He walked out. Joe Lang earlier this morning, are we going to change? I think this used to be called Nebraska Wind Conference. Is that right? And then we added solar, and so now we're going to add. We might, I don't know if y'all do or not, but add storage to it. That might be the next foray. But so as you can see, 26 gigawatts. That's all 4-hour lithium-ion based storage. I'm highlighting that because, at least from an operations perspective, I'm personally really excited by storage. We actually don't have that many batteries in SPP, but based on, and you kind of have to imagine what our load profile is, our wind drops, and then the amount of solar that we're starting to get, and it's starting to get built. Batteries is really a nice way to bridge the gap, and it also reduces wear and tear on combustion turbines, for instance, and having to fire up and lean on gas, quicker starting gas as well. So based on the studies that we have, the first 4 or 5 gigawatts of batteries in SPP are going to be super valuable for us. There's 2,700 megawatts of solar in Nebraska's queue right now as well. A lot of that is going to be processed next year. So about half of the numbers that I mentioned, 13.5, 7 gigs is going to be processed in the largest queue that we have on record, and that's the DICES 24 that we're starting December 8th. And that study is going to last about a year. But this is the footprint. So you can see the location for Nebraska, and it's all color-coded based on where they're at. This is what's in the queue. Now, it's not shown on here, but if you go on the website, there's a button on the very bottom. It's kind of hidden, but you click to the right, and it'll show you how much generation interconnection agreements we've actually processed. So rather than just what's in study, you can actually see what's processed, which we have over 30 gigawatts that are out of our hands. We've signed GIAs, and they're ready to get built for SPP as a region. So that's really exciting. Let me see if I can pull that. I was going to pull it for Nebraska real quick. I apologize. I should have just put it in the slide deck. Yeah, so 34 gigawatts we have processed, mostly wind and solar. So 12.8 gigawatts of wind and 11.8 gigawatts of solar we have processed. And that's SPP as a region. Let's see if I can pull up Nebraska's. Yeah, so Nebraska's, we processed 4.5 gigawatts of Nebraska GIAs. So these are executed GIAs. 2 gigs are solar and 1,600 megawatts of wind and 500 megawatts of batteries. So that's not part of the 13.5 gigawatts. So it's a lot of generation that we're not only have signed a generation interconnection agreement within Nebraska, but also what we're processing moving forward. And this shows you that second piece, second screen, but for SPP as a region, and it shows you what has been processed and where, and the size of the bubble is kind of the size of the interconnection customer. And as you can see, it's mostly wind and solar. So we've been keeping track of the Big Beautiful Bill Act and working with our members on what those impacts are. And I suppose it's really just depends on the generation interconnection customer, the overall project, and whether or not it'll survive. So we've been told different things, but we've, at least at SPP, we're trying to make sure that from a prediction perspective and understanding where resource planners, primarily NPPD, OPPD, LES, and so forth, understand and change their dynamic for their network resource profiles, that we have an understanding of what those impacts are. SPP was in kind of a different spot before the administration change, and that was primarily because we needed to have a higher, and I spoke about this last year, so we needed to have a higher, our very first winter planning reserve margin, and we needed to have that because of our risk profile has been shifting towards the winter for SPP as a region. And that was really under the Biden administration. So when you look at what's happened in the queue, so if I go back one, and you look at the amount of thermal, for many years, we only had about 2 gigs, maybe 3. Actually, some of it in Omaha was gas being built in the queue. And then that went up tenfold in the last year. But for me, it's not really the Big Beautiful Bill Act that did it. It was more the year before, under the Biden administration, we actually had the winter planning reserve margin as a region. So we needed to diversify the amount of generation we needed, and the accredited capacity of new gas is higher than wind and solar during the winter periods. So what we were seeing is we have really good wind, but sometimes the wind doesn't blow during our capacity critical hours, the top 3% in our winter season, that we really needed to make sure that we're sending the right signal. You know, I've said this before, my job, I'm fuel type agnostic. So we look at loss of load expectations and our overall profile of risk. And so we need to make sure that we're giving the tools necessary and the runway necessary for the load responsible entities like NPPD, OPPD, and LES, the data necessary to come up with what's cost effective for the ratepayers, but also whatever goals they want to actually meet and have in their resource plan. So I just mentioned that because that's come up before, when we talk about our transmission plans, which I'll talk about in the next panel, or next session, that the question is, are you building transmission for renewables or are you building it for load? But we were kind of already in a sort of a pivoting mode just because of the planning reserve margin in the winter. But that's not to say that, we still have really good solar profiles and we still have really good wind profiles. And so we're hopeful that we continue to see growth in all of those areas because quite frankly, we're going to need it. The load that we're seeing coming is massive. It's actually, it's crazy how big the loads that we're seeing. And it's not just spot loads. I think that gets, I joked about that large load is the new drinking game. But I don't want to go to the hospital because people say large load a lot lately. But it's not just large load. That's the thing, is half of the load growth we're seeing is organic load growth. And so it's not just data centers kind of get this big, because it is daunting. It's, gigawatt data centers. We actually have a 2.5 gigawatt data center. I think MISO has a 2.8 gigawatt data center in Monroe, Louisiana. Do y'all know where Monroe is? It's northeast Louisiana. There's not much. I used to do like a swim meet there. I'm from Shreveport, and there's not much there in Monroe. To put a 2.5 or 2.8 gigawatt data center in Monroe, that's going to change the dynamic of that city drastically. And so, yes, there's a reason why it's getting a lot of airtime, but I just want to mention that our load that we're seeing is growing without the data centers, without the spot loads. And so we're going to need a good chunk of this generation. Okay. Talk a little bit about automation and AI, which is pretty exciting for SPP. And we don't just use it for jokes. We've already started using automation, and the use cases are quite fascinating in where we need to head for SPP from an operational perspective, from a markets perspective. There's probably a better analogy for it. It's almost like pre-internet and then post-internet, and just how your life has changed, even with smartphones and so forth, and just certain things that that's probably a bad analogy, but it's a matter of what we're seeing was impossible but 5-10 years ago, and now we're seeing the capabilities of it's not just AI. AI gets thrown around a lot as kind of like a blanket artificial intelligence. What we're seeing is the use of GPUs. So we signed an agreement with Hitachi and NVIDIA, and so we're building out a data center, so to speak, with graphics processing units that can process things 80% faster than traditional power flow. And we're seeing that across the board. So the reason why that's a game changer is some of our models, because we have to model and represent the entire Eastern Interconnection, and as we expand to the West, we have to do the same thing for the Western Interconnection. Some of these take hours, if not days, to run. So days of computational time, and we can shrink it down to hours. Hours of computational time, we can shrink it down to minutes. And so, but it's not just speed. And so this is kind of helps you see, like, model solve the months that we're here. So it used to take almost a year to do model solves, and now we can shrink it down to 2 months. So we shave off 10 months. And some of the technology that we're already employing is like self-healing models. So rather than an engineer running a model and it does a non-converge and it breaks, and then you have to go in and you have to troubleshoot and figure out, I need to put more voltage support and link in, to be able to solve this particular mapping. And we actually have tools now that can do that automatically and just keep moving forward because it knows what it can and cannot do, and you put it in different parameters. So that just gives you kind of a taste of what we're seeing. But for me, it's not just about speed. Speed's great. That's kind of the thing lately, is speed to market, get things faster. We need, more infrastructure. We need to get moving. That's great. What I see is a wide variety of other use cases, because now instead of spending months building models, we can actually spend more time doing what I think we should be doing, and that's more of the decision making and understanding, are we hitting the mark when we design the transmission system? In operations, for instance, we forecast wind, and we're pretty proud of it, but and I'll give you some statistics. Our error is about single digit 24 hours out. So we can predict wind 24 hours out, less than 10% in error. That sounds great, and it is pretty impressive that we could do that. I mean, you're predicting wind at 80 meters across West Nebraska within an 8% tolerance 24 hours out. But when you talk about 35,000 megawatts of wind, and you have an 8%, I can't do math in front of people. What's 8% times 35,000? Can y'all do it? What is it? Roughly, 3,000, 10% less than 10% of that. So, so good, 3,000 ballpark. Our largest single contingency is 1,200 megawatts. It's Wolf Creek Nuclear Facility in Kansas. So, by definition, we have to maintain a certain amount of headroom to be able to sustain the most single severe contingency, and that is typically Wolf Creek. It might be ITAN, which is another large coal plant, but when you talk about an 8% error on 35,000 megawatts of wind, then that all of a sudden becomes you're carrying 3 times a nuclear facility's worth of. Now, we don't lose wind instantaneously, so that's actually a blessing because we have good wind, and it's a profile, and it's diverse across a massive amount of geographical footprint. But when we lose wind, we call it a slow burn, and so you'll lose 2, 3, 4. We've actually seen up to 7 gigawatts loss in a single hour. And so what that means is we have to be able to make sure we have enough, mostly gas, but we have to have enough headroom to kind of pick up when that wind drops. And so I use that as a use case to say, if we can use AI and the amount of performance to be able to better crunch, can we shrink that 8% error down to 2? And that means real dollars. That means real savings for everyone, because not only are you not scrambling to fire up a bunch of expensive gas turbines, but you're also able to maintain the plan and maintenance margins. You're able to, maybe even reduce plan and reserve margins, which is a significant amount of investment reduction from a capital investment perspective if we can lower the plan and reserve margins so that all the LREs in Nebraska don't have to carry as much or don't have to build as much. And so there's so many different things that we could do because it's just more data and understanding the correlation. And that's really what AI is perfect at, is it's great at linking things together and coming up with different profiles. So it's not just this graph. I don't want to just talk about GI. It's all of the other things that we're thinking about, alarming, being able to predict. One thing from a plan and maintenance perspective, right now it's sort of queue-based where OPBD might say, hey, I need to take this resource out, and it's going to be out for 3 weeks, and it needs to be out before the winter. And so we'll try to, take that request, and we run a model, and we say, if you could just take it out maybe the first 3 weeks of November, and we slot that in. We do that, it's reactionary. Well, we could take AI and greater data sets, and we have all of the data for all the operations of all of our resources, down to 4-second data. So we have so much data. And you could predict and even optimize plan and maintenance outages for the LREs. So we could basically tell Lincoln and say, hey, we know that this resource probably needs to take outage, and we could tell you when to take it based on all of the data of forecasting wind 45 days out. That's, people don't think about that, but when we're doing plan and maintenance, we have to actually predict wind a month and a half from now, not just tomorrow. And so when you think about the large amount of data that we're talking about and the software crunching to be able to maximize the profile and accuracy of predicting wind, 45 days out, it's incredibly valuable if we can do that better. And so we're excited by that. We're starting that this year, and we're actually getting the hardware for Q1 of next year, and we're already starting to look at use cases to enhance our load forecasting, enhance our weather prediction models, enhance wind and solar forecasting. And then the next phase is to really better predict. We want to be able to get so good that we can tell the Nebraska Public Power District what would be optimal for plan and maintenance before they do. So if we can get so good to do that, and there's always got to be human in the loop. So I'm not talking about automation, just set it and forget it. But if we could take all that information and better predict it, it's a game changer. Okay, I'm gonna fast forward a little bit to CPP. I've got, what, 20 minutes with questions? Is that right? 10 minutes? Okay. Okay. So I want to talk about eras real quick. I have to say this because my wife's a Taylor Swift fan. We were in MISO's area, and Taylor Swift had just had her Eras tour in Indianapolis the day before, and we were talking to MISO leadership, and we were just sharing, hey, we need to do something. We have got to get more generation on, and they're in a different spot, obviously, with their queue and so forth, but we got together and said, we need to come up with something, and we came up with an expedited resource adequacy study, and FERC did approve it, and it was named after the Eras tour. And I thought it was kind of neat because we said generational challenge. There's a pun there, generational challenge. I know, it's bad. Hey, I'm a dad. So, so we did get it passed by FERC. I did pull some numbers for Nebraska. It wasn't a lot, but there is some generation in areas for Nebraska as well. And really what this is a one-time study. It's limited to resource adequacy needs for reliability. So it wasn't just dump into the market. It wasn't trying to queue jump. What it was really trying to do is give an opportunity for load responsible entities to catch up because resource adequacy is so critical and so quick because we really have an urgent need now, and it takes a while to build generation, obviously. So that's what we did, and FERC approved it. We just closed the window. The entire window is the entire queue for Eras is significantly smaller than the queues lately, but it is, I would say, more viable because this is generation definitely tied to load for resource adequacy purposes, and it's totaling 13.2 gigawatts in Eras. So we're proud of that. It kind of disrupted the development community, and rightly so. I mean, it's definitely something that people didn't plan for, but we're proud of it from a reliability perspective because, like I said, we need generation. There's a lot of other things that we're doing in the generation interconnection space, and it really comes down to, rather than go through each one because I don't have time, it comes down to we want to get out of the way, but we still have to be reliable, and we want to be quick. So we're kind of looking at all aspects of the generation interconnection process to be able to maximize generation opportunities. And that's where a lot of these come from. So I already mentioned Eras. Surplus Plus is another one. So if you already have existing generation, you likely already have transmission capacity because you're already running and you're connected. And so you may even have extra land. Well, maybe you can expand on that and add a CT. Or if you're a wind farm, you can add more turbines. And so that's what we're calling Surplus Plus or generator priority processing. The other one I want to just highlight is the bottom right. So when we do planning models are wrong. They're just wrong because they're system intact, and we're trying to simulate something 5 years out or 10 years out. And so when we come up with a calculated limit on generation interconnection, it's a limit based on planning models, but there are opportunities in real time to maximize the generation in real time because at that point you have some SCADA real-time measurements. You understand what the limitations are on the grid. And so what we've tried to come up with with a quarterly operations limit is we still have a mandate to be reliable in our studies and planning, but we want to give all the tools to the operators as possible, meaning they could break or exceed their generation interconnection megawatt in real time if we need it. And so I'll kind of leave it there. It's just more of we're trying to figure out, okay, how can we legitimately allow for generation to go above their GIA in certain timeframes, not just emergency situations, because we just need every megawatt we can get. Okay, with the remaining time before questions, I did want to talk about CPP. This is a game changer, and we're quite proud of it. Again, it's been about 4 years in the making. JTIQ was I would say the infant part of it, so the joint targeted interconnection queue lines that we worked with MISO to perform. JTIQ was born out of really the CEO at the time, Barbara Sugg of SPP, and then John Baer, he is the CEO of MISO. They got on a call. It was the thick of the pandemic. I know all of us were probably at home at the time. It was like 2 or 3 months into 2020. And they got on the call and they said, forget what's in the tariff, forget what's in coordinated system plan, forget what's joint operating agreement, design the lines that we need from an engineering perspective, and then we'll figure out cost allocation after that. So rather than be held accountable to models and different processes, we got the teams together from SPP and MISO perspective. We planned the system first, and then we came up with the cost allocation rules after. And what we did with JTIQ is that really started to morph into how could we do some concept like that with the generation interconnection process within SPP, and that's what we came up with consolidated planning process. And so I'm going to try to give the elevator speech here. Going back to the highway analogy, where you're the last car that broke that traffic needed to expand, and you get hit with the bill, and obviously none of us can afford to just build a highway. And so what we're doing now with CPP is we're planning the system 20 years out. No construction, no notice to construct, but we plan the system 20 years out. And we're leveraging all the members' data. So as much data as Lincoln and NPPD and MEAN and others, OPPD can give us, we model that, and we try to predict out the future and build out the system from a model perspective. Then we come up with what's called the grid contribution fee. We again love our acronyms. Generalized rate for interconnection development. So GRID, generalized rate for interconnection development contribution. And so what we do is we calculate that fee, and if you're a generation interconnection customer and you're looking to connect to SPP, you still have to do all of your due diligence. You have to have site control, and you have to do your study deposit. And you have to have all of the things necessary to get into the queue. But you pay your grid contribution fee. You know what it is up front. There's cost certainty. There's schedule certainty. We still have to calculate the incremental costs for your we call them generator outlet facilities, but the local lines necessary to connect reliably. But you don't get hit with the highway costs ever, because that's what your fee is. Your fee represents your contribution to building out the highway, which is ultimately the extra high voltage transmission facilities that we're building. The reason why this is a game changer is we won't have restudies. We won't go back into a backlog. If you're not ready, if you're a generation interconnection developer and you're not ready, you just go to the next cycle. And so the beauty of that is the schedule and cost certainty, but then what we do is on an annual basis, so we do the 20-year look every 3 years. And then within the year of those 3 years, we come up with an actual transmission plan that will build out the system to accommodate not only the generation interconnection customers, but also load growth as well for reliability, economics, and public policy needs and persistent operational needs. And so that's really the game changer of CPP. It's a 500-page tariff change, so it was pretty significant, very involved, lots of costs and financial obligations and so forth that were lined out. It doesn't disallow you from connecting to a unplanned site. You would just be hit with incremental costs above that. So if you connect to what we would call suboptimal site, it's still open access transmission. So we're still maintaining the integrity of the tariff and what FERC is mandated to do from an open access perspective, but you would just get hit with the incremental costs above your grid contribution fee. And so it's a streamlined assessment. It saves time, it saves money, it gives upfront cost certainty, upfront schedule certainty for all the customers involved. It was 100% unanimous. This was phenomenal. Every single person, every single sector, the board, the regional state commissions, the commissioners, all the sectors, so developers of generation, public interest groups, the load responsible entities, transmission owners, everyone, they all voted for CPP. We're working on, we actually just finished up some testimony and so forth yesterday. We're going to file with FERC, I think, next week. And so we're real hopeful that we're giving them 120 days because it's such a big deal. But we've been working with FERC staff and FERC commissioners for a number of months now, and they're chomping at the bit to see the final product. And what I predict is that they will approve it. And I think that, what is it, mimicry is the best form of flattery. I think PJM and MISO and others are going to take this up, which I'm a little bit jealous of, because they're not going to spend 4 years on it. They're just going to take it and modify it. But oh well, that's the name of RTO. We're nonprofit, so we don't make any money on this, but it's certainly we're proud of it. Okay, I think yeah, that's just the timeline of CPP. This was just, and I think these slides get shared, so you can, there's a lot of different milestones and things that if you're interested in, but I like this slide just because it helps illustrate the actual golden diamond that we're seeking for GIAs to be issued, and so various opportunities to get more generation through SPP. With that, do y'all have any questions, or did you have questions for me, or?
I have no questions yet, but we could take some questions from the crowd. This gentleman in the middle.
Thanks, Casey. It's always enlightening to hear you. Could you say a little bit about where SPP is at implementing dynamic line rating, and when that's done, what the impact will be? Will it mean more can be interconnected, or will it just mean less congestion charges? What will be the practical impact when that is implemented? And how far, to what extent is it implemented now?
Yeah, so there's two distinctions there. One is the FERC Order 881, which is the ambient air ratings. And I believe that's intended to go live next year, so in 2026. That's a little different than dynamic line rating. So dynamic line ratings, we are encouraging people to use, but that's not actually required in SPP, and so it's solely based on the transmission owner and whether or not they want to go through additional rigor. So dynamic line ratings is not just looking at ambient air changes, it's looking at all the different conditions that it could provide. Planning models don't use dynamic line ratings and ambient air. We've worked with the membership to determine, do we want to? You know, we do simulate the market, 8760 runs, so all hours of, let's say, year 5, to do an economic run to kind of simulate what the market's going to do. And we've discussed with our membership, do we want to somewhat simulate air? I mean, we know that 5 years from now, there's going to be cooler days, right? And so you could theoretically calculate that. Maybe it'll come with more, like what I mentioned from a data set perspective and AI perspective, but at least right now, we're taking the conservative approach in the planning models. So to answer your question on the real world impacts, we would still necessitate the seasonal ratings in the planning models and not simulate the dynamic line ratings in the planning models. So it really comes down to real-time event management and congestion reduction. So we should be able to maximize the output of wind, for instance, with dynamic line ratings, because obviously it's intuitive that if it's windy, then hopefully, you know, you're not, it's not too hot from a conductor perspective. It has a lot to do with what is the limiting element on the transmission system. But this is a whole separate piece that I might get into on the next session. What we're wanting to spin up, or we're spinning up a group called the Intermediate Planning Group at SPP. It's going to take 6 years to build some of these large EHV facilities that we need in SPP. And we can't wait. We can't wait 6, 7 years. We have an urgent need now. And I'll tell you, I'll just cut to the chase. Our 10-year model of load last year that drove our largest transmission portfolio is now our 2-year model. So that just kind of gives you a basis that this load is growing, but it's not just growing 10 years from now. It's here today. And so we're going to have to do more than just what FERC asked us to do with 881. We're going to have to work with our TOs and come up with clever ways to not just use dynamic line ratings, but also grid enhancing technologies, maybe issue notice to constructs on low-hanging fruit, and maybe remedial action schemes. We're going to have to be very clever about how we can maximize the transmission system today while we wait for the next layer of infrastructure to be built. Great question.
Thank you. I really commend the work that SPP is doing on expediting the process. It's really important. With all the growth, transmission's about always the pinch point. And there's a lot of discussion. I don't know if EHV equals 765 lines, but there's a lot of discussion about that, and it's a horse of a different color. We don't have those here. Is SPP looking at how that can be built out across the entire footprint and then the costs allocated
Yes.
accordingly?
Yes. I have slides on the next session. So if you could just, are you going to stay for the next one? Okay. If you could just wait on that. The answer is yes. And we do have a plan. I do have a slide on it, and then we can talk about it a little further in that one. Yeah. Yeah. Little teaser.
I have a question over here. I'm over here.
Oh.
The reserve margin went from 12% to 15%. Why is that, and do you expect that it will continue to grow?
So it was driven by basically the performance of the resources coupled with load growth and basically our load profile changes. So it was a combination of things. Basically, our risk is challenging in both the summer capacity critical hours and the winter. Now, I'm going to give you a little data point that hasn't been released yet because we're still, but we've gotten some preliminary analysis. We do a loss of load expectation study, and loads are changing rapidly. The profiles are changing rapidly, but also the new gas that we're getting in particular is better performing. It's almost like buying a new car. So hopefully your new car starts when you buy it off the lot. And so it's basically a combination of all of those things may levelize the plan reserve margin. So I'm going to cut to the chase and say hopefully it doesn't go up because of those information. We're actually presenting that to our supply adequacy working group I think later next month. So
Question, Casey?
yes.
Over here.
Hey.
First, a heartfelt congratulations on getting from the traditional reactive, trying to figure out how to do interconnection requests on your existing congested system to being proactive, looking forward. That's an incredible accomplishment. And do you have any sense of what the capital outlay is looking like on these 10-year projections that's going to get spread across all of your LREs?
For transmission or
Yeah.
for transmission? Yeah, it's hard to tell. Right now it is billions is what we're looking at across the footprint. And load is growing across the footprint. It's in my slides next session, but it'll help illustrate that, this particular transmission planning cycle has a lot of loads in the southern part of SPP, but next year actually has loads growing across Kansas, Nebraska, South Dakota, and North Dakota across it, which is helpful from a cost allocation perspective, but it also illustrates the need just across the board. But it is orders of magnitude bigger than what we're used to seeing.
Hello. Do you know the typical times from GIA issued to GIA executed? And is it something that has improved in the last years or not?
Yeah, so GIA issued versus GIA executed, it really depends. It depends on the customer, it depends on the negotiation, and where we see some that take just a few months, we see some that are even longer. So it just depends if those parties are ready to move forward. So, yeah. Are we done?
Hi, Casey. A real quick question. As a former portable nuclear operator, you say reliable as much as I used to. Why do we see such a dearth of development in the vicinity of the DC ties, not only because of the seam between the grids, but the significant amount of transmission assets at those locations that could be potentially used to wheel power in multiple different directions, supply chain issues notwithstanding? Why do we see such a vacuum in that area and the heat map is in other areas where the loads are at?
I don't know. You might want to ask, where's Lee? You might want to ask the Invenergy developers and so forth. That this is a lot to unpack, that question. But so I'll try to be brief. So we're expanding to the west. SPP's expanding to the west. We'll have at least at first 3 HVDC back-to-backs, 3 of the 7 to the Western Interconnection. We do have 2 back-to-backs with ERCOT, the only 2 that ERCOT has. Then you have all these merchant HVDC facilities, Grid United, Invenergy, Nextera. There's a few of them that are trying to build these large facilities. I say it almost like Plains and Eastern Clean Line 15 years ago. They tried to do something. I think it's much more viable now. I think the need is there. What SPP is looking at is how can we be a part of that solution rather than it just happen to us. We want to be a part of it, and we want to say, okay, is there a way that we could cost share in some of these facilities where it would be in lieu of additional transmission? So we could say, is there a way that we can be, since we're independent as an RTO, it would require a TO like Lincoln or Nebraska Public Power District to be kind of party to that. But so there's a lot of complexity around the agreements that we would come up with. But what we're seeing is there is a significant amount of value to either expand the ties or jump the ties or join the interconnection or just embrace some hybrid to where maybe some of these merchant facilities actually happen and we join the ties. And we've already done some reliability studies where it is very possible. Most people don't know, but in the 60s, they were connected. And so the interconnections were connected. We've since built out the transmission system. It had all these stability limits, and so that's why they disconnected. What we're looking at is, as we expand to the west, what is the basic strategic plan and overall vision for how we build out the system, not only for the 765 overlay or other voltages that was mentioned, but also how do we make sure that we're future-proofing what that expansion looks like. But I think bottom line is there is a lot of value to these lines, but they're also very expensive. So it's just a matter of hopefully some of them get done.